So today we are very happy to have Yiming Chen from Stanford, and he's going to tell us about chaos and fortuity of holographic BPS. So you can start, Yiming.
Okay. Thanks, Raghu. Thanks for having me today. I look forward to visit there one day in person. So today I will be talking about a series of recent work that I've been doing about chaos and fortuity of holographic BPS states. So mostly the talk will be based on a paper I wrote earlier with Henry Lin and Stephen Schenker, and the upcoming paper, which hopefully will come out this month or early next month, with Yiming Chen, Bixun Xie, and Zhenping Yang, all in Tsinghua University in China. Okay, so let me start with some general motivation and general background. So during the last decade, we've learned a lot about this remarkable connection between black holes and quantum chaos. So let me remind you that one of the universal features of a chaotic quantum system is the random matrix universality of its spectrum. Now here I'm drawing schematically a spectrum of some microscopic system. So you have many individual energy levels. And one feature of the random matrix universality is that if you look at the spacing between the nearest eigenvalues, you see the existence of the so-called universal level repulsion. Namely, there is an effective repulsive force between the eigenvalues. This was first discovered by Wigner and Dyson. Now, a convenient way to see this repulsion is to plot the histogram of the spacing between the eigenvalues. So I can collect all the spacings between adjacent eigenvalues and look at the histogram. And for a chaotic system, it will satisfy this red curve, which is the so-called Wigner surmise. So the key property is that it starts out at 0, meaning that it has vanishing probability for two eigenvalues to be very close to each other. And then it grows and decays. On the other hand, for an integrable or non-chaotic system, the distribution starts out large and then decays, and generically it follows a Poisson distribution. Now, it is expected that black holes, just as other chaotic quantum systems, also exhibit this universality. In the past few years, this has been better understood how to see this universality from gravity. So one way to see it is by studying a universal double cone wormhole geometry in gravity. So this is a very nice story, but today I won't have time to talk about it. Even though chaos is very universal, it is always constrained by the global symmetries that you have in your theory. Now, usually symmetries do not eliminate chaos. What you need to do is to focus on particular representations, and then you discover chaos again. On the other hand, a particular powerful symmetry, which is the so-called supersymmetry, appears to completely forbid chaos, at least at the face value. Now, what we need to know about supersymmetry is that when you have this symmetry, the energy of a quantum state is bounded from below by a so-called BPS energy that is completely determined by the conserved charges in your system. So this is the so-called BPS bound. And for states that preserve this symmetry, preserves the supersymmetry, they saturate the BPS bound. In other words, instead of having this non-BPS individual non-degenerate microstates, we will have a degenerate subspace of states with exactly the same energy. In other words, the energy of the BPS states are completely determined by their charges. So we simply cannot have any level repulsion. Now, if we fix the charges to be large, let's say in a large n system, we fix the charge to scale with n, then we would generally have a very large degenerate subspace of BPS states. The number of states can grow exponentially in n. The question that we want to talk about today is whether the notion of chaos is truly absent in this setting, or can one still find some chaos here? Now, before I go into this question, let me give you several motivations for thinking about this problem. One of the motivations for us is that in the literature, there has actually been a lot of confusion or debate about this topic. The main reason is that at the same time, in the quantum system that you focus on these BPS special states that saturate the BPS bound, there is also a breakdown of universality in gravity when we have supersymmetry. So instead of very generic picture of black holes capturing the physics of non-BPS states, once you go to the BPS bound, it seems that depending on different situations, you can have completely different descriptions for the BPS states. So in some cases, it's known that all the BPS states are described by supersymmetric solutions that are horizonless. So here I just drew it very cartoonish as this some configuration without the horizon. While in many other cases, in fact, it's known that in gravity, the solutions capturing the BPS states are supersymmetric black holes. Now, here it seems that at least within this context, you can have many different possibilities for the bulk description. And the possibility of having high energy states without horizons has been sometimes viewed as an encouraging sign for constructing these so-called black hole mimickers. These are sometimes also called microstate geometries, or more generally goes under the name fuzzballs. But this proposal sometimes has been dismissed based on the presumption that maybe the BPS states are too special. They lack some of the important physics that we would like to discuss for non-BPS states, such as quantum chaos. So maybe only for this special case, you find these special geometries. Now, one of our goals in this work with Henry Lin and Stephen Schenker is to try to do some calculation and clarify some of these issues. By the way, also feel free to stop me at any time and ask questions.
A question about the previous slide.
Good, yes.
I didn't fully understand. So this black hole mimicker, you're just referring to the fuzzball proposal, right?
Yes.
If the BPS states, if the thinking was that BPS states don't have chaos, then that's good for fuzzball, right? Because they say, oh, we don't have a horizon, so maybe it. So, but your second sentence is a bit confusing to me.
So here, what I mean is that if BPS states don't exhibit chaos, really don't exhibit chaos, then you might think that these fuzzball pictures might be difficult to generalize to non-BPS cases, where you expect a completely different physical picture.
Oh, I see. Okay.
So I will view it as a counter argument for the fuzzball proposal. But,
okay.
Yeah, but that's will not be the conclusion, at least not a complete conclusion of this talk.
Okay. Okay. Thanks.
Okay. Now, let me also give you another motivation of thinking about this chaos in the BPS context. Now, as is well known, one of the main reasons to study supersymmetry in theoretical physics is that it usually brings us some extra tool, powerful techniques that opens a unique window into strongly coupled quantum systems, which we might not be able to access otherwise. Now, as an example, the counting of the number of BPS states through the supersymmetric indices is a very rich and well-developed subject. Now, I want to draw your attention to some interesting, exciting new development in this direction. There has been some exciting recent progress in not just studying the number of BPS states, but also the explicit cohomologies, and in fact, sometimes wave functions of BPS states that describe black holes. Now, here I'm just taking a screenshot from a paper by Pedro Vieira et al., where they show you what is the so-called black hole wave function in n equals 4 super Young Mills for the very small n equals to 2. And the black hole wave function takes this following complicated form. Now, this is a subject that is still rapidly developing and is still at the early stage, but I think it would be interesting to ask what kind of physics can we extract from these kind of expressions, whether we can extract some interesting physics out of it. So that's a different, another motivation for us to think about these BPS states. Now, before I jump into the main content of the talk, let me just give you the take-home messages.
Now, I have a question about the previous slide.
Okay, good, yeah.
So this thing that you're writing is some operator with some specified charges, right?
Yes.
And this was supposed to be some 1/16 BPS? operator?
this is a particular 116 BPS states that is fortuitous. So I will discuss this notion of fortuity in the later part of the talk.
Okay. But just
But
by sorry.
There is a reason why this particular state is, well, quoted as a black hole state compared to other BPS states.
Okay, so maybe I'll ask when you cover it. Okay.
Sure, yeah, good. Okay, good. So now let me first tell you what the take-home messages of this talk are. Now, the first message I want to convey is that BPS states can be chaotic, and I will tell you what the notion of chaos is. And in this notion of chaos, I will argue that some BPS states are in fact as chaotic as generic non-BPS states. So they're really some of the BPS states in this regard are really not special and not distinct from the non-BPS states. On the other hand, we do find that there are sharp distinctions between the microstates of horizonless geometries, at least for a large class that that are well understood, and the microstates of black holes. So one of such a sharp distinction that I will argue is that they exhibit disproportional amount of chaos. Namely, I will try to argue that the microstates of the black holes are much more chaotic than the microstates of the horizonless geometries. Now, in the second part of the talk, I will connect these different fine-grained feature of chaos to a very interesting recent classification of BPS states as monotonous versus fortuitous. Good. So let me start with the first part of the talk, where I will tell you what the appropriate notion of chaos for the BPS states are. So just in general, in a quantum system, you can discuss various different notions of chaos. One of such notion that I already mentioned is what I will call here simply as eigenvalue chaos, which is this random matrix statistics of energy levels. Now, as I already said, this notion does not apply for the BPS states, which all have the same energy if you fix the charges. On the other hand, there is a closely related but distinct notion of chaos, which is the so-called eigenvector chaos. What does it mean? So the idea is that if you look at a quantum chaotic system and look at its eigenstates, the idea is that the eigenstate will resemble random vectors with respect to simple operators in your theory. Now, let's say we are considering a holographic CFT, we can simply take the simple operators to be a conformal primary with order 1 conformal dimension. That would suffice as a definition of a simple operator. And one way to quantify this random vector property is through the so-called eigenstate thermalization hypothesis, meaning that we look at the matrix element of operator O between two energy eigenstates, EI and EJ. And the statement is that up to a smooth piece that is proportional to the identity, we have highly fluctuating noise that are exponentially small. So they go like e to the minus s over 2, well, s is entropy, times a matrix Rij that essentially behaves like a random matrix. Okay. And we can apply this notion of chaos for the BPS states. The idea is that even though for the BPS states, we don't have these individual eigenstates anymore, they are all degenerate, but we can say that this BPS subspace is a random hyperplane, so some sub-Hilbert space in the entire Hilbert space that is random. So one way to quantify or to make this more precise was already proposed by Lin, Maldacena, Rosenberg, and Shan in 2022, which we call the LMRS criteria. So the idea is that we define the projection operator P sub BPS as an operator that projects us into this subspace. And we can sandwich a simple operator O in between two projection operators, consider POP, and define that as some projected operator O hat. Now, essentially following the same idea of this eigenstate thermalization hypothesis, the projected operator would be basically this random matrix Rij up to an identity piece that we can subtract off. So we simply take the definition of chaos in the BPS subspace as for generic simple operators, the projected operator O hat shows random matrix behavior. So this will be the notion of chaos that we will use for the BPS states in today's talk. Now, how do we know whether O hat shows random matrix behavior or not? As I already mentioned earlier, one way to look at it is to just study the nearest neighbor spacing in a spectrum. And you will find either generically speaking, you will find either the Wigner surmise or some Poisson distribution. Now, I want to emphasize that this criterion, by just looking at the nearest neighbor spacing, is in fact a very, very weak notion of chaos, because the level spacing only probes the existence of chaos at the finest possible scale, because they only look at the level repulsion between adjacent eigenvalues. And adjacent eigenvalues are extremely close to each other. They are exponentially, their spacing is usually e to the minus s. So it's a very small energy scale. So it turns out that this very weak criterion of chaos is not enough to distinguish horizonless geometries microstates from black hole microstates. So to improve this discussion, we borrow some further idea from this random matrix literature. The idea is that one can further quantify what I would call the quality of chaos, or how strong the chaos is, by looking at the energy scale, which is roughly speaking how far the level repulsion propagates in the spectrum. Now here, the idea is that the eigenrepulsion, the level repulsion does not get screened just at the level of a nearest eigenvalues. It propagates to certain energy scale in the spectrum, which is usually called the Thouless energy scale. Okay. Now let me give you some examples. Consider this plot that everyone is familiar with, namely just a random draw from an actual random matrix ensemble. There you will in fact find the Thouless energy scale is of order 1. So here order 1 means that if you pick an eigenvalue that is at the left end of the spectrum, its level repulsion propagates until the right end. So the Thouless energy scale compared to the total span of the spectrum is order 1. On the other hand, if you consider a weakly interacting system, such as a weakly interacting graviton gas, usually you expect very weak chaos, meaning that the Thouless energy scale, the extent where the level repulsion propagates compared to the total span of the spectrum is suppressed in the large N limit. So let's say it usually decreases as some power of n, like 1 over n to the some power alpha, positive power alpha. And it goes to 0 in the large N limit. So in this talk, we will use the scaling of Thouless energy as a criterion for whether the chaos is strong or weak. So we say that the chaos is strong when the Thouless energy is order 1 in the large N limit, while the chaos is weak when the Thouless energy goes to 0 compared to the total span of the spectrum in the large N limit. Now, in practice, in fact, it is
a question about the naming of this. The references you cite don't have the Thouless in it. So is this, do you know what's the history of this naming or?
Good. So it partly is maybe because maybe my citation here is not super complete. So Thouless first studied this Thouless energy in let's say lattice systems, and these people study these maybe more generically in random matrix literature.
I see. So these references were later than the.
Yeah, these references are later, if I'm not mistaken. Yes. Good. And in practice, it's more convenient to study the inverse of this energy scale, which is the so-called Thouless time, which can be extracted from a quantity that is the so-called spectral form factor. So I won't go into detail of how you do this in this talk. Now with this, hopefully I convince you that there is this very sharp criterion that you can apply for BPS states. And then we can ask what one might expect, whether the BPS states are chaotic or not, or how chaotic they are. Now, in fact, for supersymmetric black holes with ADS2 throat, people have already done some of these analyses, which suggests that the BPS subspace, in fact, exhibits strong chaos. Now, one of the study was by LMRS. Well, they studied this projected operator and its spectral form factor using techniques from the JT and Schwarzian effective theory. So their analysis suggests that the projected operator, in fact, is very much resembles a pure random matrix. So it has a very strong chaos. I want to also mention that there has been recent nice work by Turiashi and Witten that proposed random matrix theories with n equals to 2 supersymmetric ensemble. So if you assume this is the correct universality of your quantum system, then this random matrix ensemble also implies strong chaos for the BPS states. On the other hand, the horizon-less geometries appear to be highly structured. In many well-understood cases, the horizon-less geometries are usually characterized by several explicit smooth profiles of supergravity excitations. So intuitively, one might expect them to exhibit less chaos. They are not like the random states that black hole microstates are. But this is just a very vague intuition. So in the next part of the talk, we will try to really quantify this and do some calculation to demonstrate. Now, let me go to this part of the talk. We will study some cases of horizonless geometries in the case of n equals to 4 superior mules theory. Now, in our paper, we also studied some stories in the D1, D5 CFT, but I'll refer you to our paper and not go into that today. Now, for the n equals to 4 superior mules theory is a very, very rich theory. It has many supersymmetries. So depending on what fraction of supersymmetries that you preserve, you can divide the boundary theory into various subspaces. So here I'm dividing it into 1/2 BPS, 1/4, 1/8 BPS subspace, and the least supersymmetric case is the 1/16 BPS case. Now, depending on which sector you are in, the known bulk solution, as I said, is very different. In the first three cases, to my knowledge, all the known bulk solutions are horizonless geometries. There are the Lin-Lunin-Maldacena geometries, these so-called bubbling geometries, and their generalizations to the lesser supersymmetric cases. On the other hand, for the 1/16 BPS case, the known bulk solution are supersymmetric black holes that carry many charges. So in our paper, we mainly focused on the 1/2 and 1/4 BPS sectors where we are able to do some calculation and study this question about chaos. Now, both of these cases are described by horizonless geometries. Since our discussion is trying to do the calculation in the boundary theory, we are limited by our ability, so we are only able to study the theory at weak tooth coupling limit, namely take lambda to be much smaller than 1 and work at one loop. But let me mention that this notion of strong versus weak chaos has to do with the n scaling. So we think that is the reason, even at weak coupling limit, one might already expect to see some interesting differences between these various cases. Now, before I tell you the detail, let me tell you what we found. Now, one thing that surprised us is that even the horizonless geometries exhibit chaos. We didn't really expect this before we started the project, but indeed we find that they are not completely not chaotic. However, we do find that the highly structured nature or this feature of these solutions lead to ways for us to quantify their thoughtless energy or thoughtless time. And we are able to argue they exhibit very long thoughtless time, meaning very, very weak chaos compared to the strong chaos of black holes. Now, let me for the next 15 minutes or so, let me tell you about, roughly give you a flavor of what we did in our paper. Now, let me start with the simplest case, the 1/2 BPS sector. Since here we are studying a gauge theory with adjoint matter fields, a basis for the states or operators are simply gauge invariant words built out of letters. And the 1/2 BPS sector is particularly simple in this regard. You simply take all the multi-traces, excuse me, all the multi-traces formed by only one letter, Z. So Z is some complex scalar in the theory. So you take various traces of multi-traces of these Z's. Now, a particularly simple feature of this BPS sector is that these states, they do not develop anomalous dimensions as you turn on the tooth coupling. So these are the BPS states in the free theory. They are also the BPS states in the interacting theory. So the first step of finding the state is very simple here. Now, the second step is that we want to project the simple operator into this subspace. So naively, you will go and try to compute matrix elements of this sort. The cat state is some multi-trace of Z's, while the bra state is some charge conjugate involving Z bar. But one subtlety comes in here, that is, we are interested in very, very high energy states. So for super mules, this means that we take energy to scale as n squared. So in this regime, this multi-trace basis is really awkward to work with because they become highly redundant due to what is called the trace relations. So here, the trace relations just come in a technical way, but later in the talk, I will tell you some more important consequences of it. But here, let me show you an example. Consider the energy equals to 3, meaning that we have 3 units of energy. So we can put 3 Z's. Naively, we can write down these 3 states, trace Z cubed, trace Z squared times trace Z, and the third power of trace Z. So here I'm considering the UN theory. So here I can have a non-zero trace of Z. Now, these 3 operators, they are linearly independent when n is greater than 2. So you have 3 states at this level. However, when you take n to be small, when n is smaller or equal to 2, there is in fact an identity, an operator identity that relays them. So this naive basis that you wrote down becomes overcomplete. Now, this is a huge problem in this region where energy scale is n squared. Most of the states that you write down will be not independent of each other. So even if you compute these matrix elements, it's kind of awkward to work with. Now, in the 1/2 BPS case, there is a very nice description that actually get rid of this redundancy. So let me quickly tell you about it. The idea is that you can rewrite the 1/2 BPS states in terms of states of n fermions in a harmonic potential. So I'm drawing here a harmonic potential. You have many levels in it, and you just put n fermions in it. That furnishes a non-redundant description of the Hilbert space for the 1/2 BPS states. Now, how does this translation goes? The ADS vacuum or the identity operator in the CFT is simply mapped to the Fermi C state. So in the harmonic potential, you occupy the lowest n possible levels. What about the single trace operator? So if we have a single trace operator, trace Z to the K, that in terms of the fermion language excites the fermions by K units of energy. So ignoring this coefficient here, in terms of fermion operator, it simply removes a fermion from the Lth level and put it back to the L plus Kth level. And we can multiply these traces successively. That means that we excite the fermion system more and more. And roughly speaking, different horizon-less geometries correspond to different ways to excite these fermion systems, or different highly excited states in this fermion problem. Good. Now, let me emphasize one thing, is that here, because we consider energy that is very, very high, we are considering a subspace of fermion states with energy of order n squared above the Fermi C state. So on average, each fermion are excited with energy of order n. So we are considering a subspace of states in this fermion problem with the fermions very highly excited. They are usually very far apart from each other in the energy. Okay. Now we can, with this non-redundant description of the Hilbert space, we can ask how we can revisit this problem of projecting simple operators. Now, what are some simple operators that we can play with? For super mules in the free limit, because we do our calculation in the free limit. In fact, we use the free theory weak contraction to evaluate the matrix elements. Many letters simply do not contract with the cat and the bra. These cat state and bra states that only involve Z and Z bars. So we can restrict our attention to a subclass of operators that do contract non-trivially, those are operators that are built out of z's and z bars. For example, one can consider a bound state of two gravitons, which would be an operator of this kind, trace z bar square times trace z square, normal ordered. We can also consider more generic operators, let's say operators that are roughly speaking due to string states in the bulk. So there are trays of z's and z bars ordered in various different random ways. So let me tell you the general result. So if you consider projecting an operator, just a multi-trace operator of this type, but importantly with order 1 many letters, one can show that the projected matrix, a projected operator in terms of the fermions, boils down to an order 1 number of moves. So what do I mean by a move? So each move basically shifts the energy of one fermion by some order 1 amount. Okay. In other words, this projected matrix just chooses order 1 many fermions in this n total fermions, change their energy by a little bit. Let me give you a concrete example. Look at this operator, trace z bar square times trace z square. Now this operator, if you write it down in the fermion language, it boils down to an operator that contains two moves. So roughly, basically, it increases the energy of one fermion by 2 units and decreases the energy by another fermion by 2 units. In fact, in this case, you can find the spectrum of this projected operator analytically, and you find the spectrum with huge degeneracies where the eigenvalues are basically regularly spaced. So this is a spectrum that would be dramatically different from a spectrum that we expect with chaos. More generally, though, if you consider general operator of this type, the degeneracy will be lifted. And if you just look at the nearest neighbor spacing, is you in some cases you do find Wigner surmise. Now what happens is that we can argue that these operators, this general class of operators only exhibit weak chaos. The idea is that the projected operator, as I mentioned, because it boils down to an order 1 number of moves, and there are so many fermions, it only takes a state to its nearby state, meaning that it cannot change the distribution of these fermions too much. This means that the matrix will actually be what is called a banded matrix if you order these half BPS states in some smart way based on their some of their features. What do I mean by a banded matrix? So here I'm drawing actually just a particular example where you see that the projected operator only has non-zero elements extremely close to the diagonal, and elsewhere is completely zero. So again, the reason of this is because when you act this matrix on a state, it only takes you nearby. It does not take you very far away. You can actually quantify the width of this band and compare it with the total size of the matrix. In the large n limit, you find that it decreases at some power of n, like 1 over n to the 3 halves. Now, in the random matrix literature, people have studied the property of this kind of banded random matrix. And people found that such an operators, even when it is chaotic, it will have a very long Thouless time, a Thouless time that grows as powers of n. Here, that a lower estimate for the Thouless time will grow like n cubed. Okay, so this is an argument why, in this case, we only find weak chaos. Was there a question?
Yeah, so this 1 over n to the 3 halves is some relative factor between the total size of the matrix and the width.
Yes.
Uh-huh. And
Yeah.
so one thing, so you said that, is it correct that even if you took this trace with multiple z's and z bars inside,
Yeah.
it would still be a banded matrix? That's what you're saying.
Yeah, that's what I'm saying. Yes. So more generally, you can't show that the matrix does not exhibit chaos like this plot. In general, you can't find its eigenvalue analytically, but you can use this argument, this banded matrix argument, to argue that even if it is chaotic at the nearest neighbor level, it will have a very long Thouless time or very small Thouless energy.
We expect that similarly, if you went to 116 BPS, this bandedness will go away.
Yeah, we expect that. I explain that later
Okay.
through some indirect arguments. Good. So let me quickly tell you what goes on in the 1/4 BPS sector. So I want to talk about this because there are some interesting new features here. So the 1/4 BPS sector in the free theory is not that different. So in the free theory, the BPS subspace is just that instead of one letter, you take two letters, Z and X, two different complex scalars, and you form multi-trace of this kind. So that builds the free classical BPS states in the theory. Now, what's important here is that the analysis is much more difficult because as you turn on the tooth coupling, even infinitesimally, most of these states will be lifted. So you only get a very small number of BPS states that remain BPS at one loop. So this is saying that we have a non-trivial one loop problem to solve, where we have a one loop Hamiltonian, or in this literature, in fact, usually called the one loop dilatation operator, which takes the following form. Now, this is a fascinating problem to study in its own right. And well, if I have time, I'll tell you a lot more about it. But because this problem, the infinite n limit is famously integrable. However, here we are in fact studying this problem in a completely different regime. We are taking the energy to scale as n squared. So it's in fact a very chaotic quantum system. So it's an interesting problem that interpolates between the two limits. Now, there are various ways to approach this. We discussed this in our paper. Now, today, let me just show you some of the most concrete results. That is to attack this problem numerically. So we can actually put this degenerate perturbation theory, meaning start with all these free BPS states and study the one loop problem. We can do this numerically on a computer. So let me show you the result for SU4 gauge theory, and with number of Z's and number of X to be relatively large. Let's say number of Z's to be 14, number of X to be 7. Now here I'm showing you the anomalous dimensions in the horizontal axis, and the vertical axis are just the number of states. And in this plot, you can see that there are some states with 0 anomalous dimension. So these states are the one loop BPS states. These are the states we want to study in this projecting story. While in the same calculation, you also get this continuum. So a continuum of states that are non-BPS. Now, the first thing you can check here is that the lifted states, these non-BPS states, they are chaotic. So the reason is, as strong coupling, we expect these non-BPS things to eventually become black holes. Now, for the non-BPS things, you can just apply the old-fashioned eigenvalue chaos. You just look at the eigenvalues of these non-BPS states and look at whether they exhibit Wigner surmise. And indeed, you find the level spacing agrees with the Wigner surmise of a GOE example. Now, what we are mainly focusing here is the BPS. Yes.
Sorry. So this number that stays at 0, this 21 or something,
Yeah.
is that also equal to the index at the free limit?
Yes, yeah, you can compute these from the index, yes.
Okay, so that just stabilizes at that when you turn on the coupling immediately.
Yeah, it's conjectured that the number of BPS states is in fact one loop exact.
Okay.
I think in some earlier paper by Shiraz and collaborators. Good, and okay, I was on this slide. Yes, so in this talk, we're mainly interested in the BPS states. So we can pick a simple operator O. So I didn't tell you why this particular choice. So this choice is mainly to get rid of some symmetries. So there are some symmetries in this problem. We want to find an operator to commute with all the symmetry generators. So you take this operator and project it into the BPS subspace. Then you can look at the level spacing of the projected operator. You find a distribution that looks like this. It looks mostly follow a Poisson distribution with some excess in this intermediate spacing. So we, in fact, expect this excess to be due to some regular structure in the spectrum. So we think this is, in fact, a sign that the projected operator is not chaotic instead of being chaotic. So mostly it follows a Poisson distribution. Now, if I just have this plot, it might not be extremely convincing, but in the same calculation, you can project the same operator into the highly excited energy window. that you find that the projected operator satisfies the Wigner surmise. If you in fact project it into the near BPS states, so these low-lying states, you sort of see a distribution that is in between Wigner and Poisson. So something that interpolates between these two limits. Now, with more generic choice of simple operators, we do expect weak health, similar to the 1/2 BPS case, meaning that at the nearest neighbor level, we will find a Wigner surmise. But in our paper, we used a coherent state representation of quarter BPS states to analytically sketch an argument for why the Thouless time similarly in this case is very long, grows with n in some power. Okay. Just as a side note, I want to say that here, as you see here, when you go from non-BPS to BPS, even in this very toy kind of one loop calculation, you see the slowdown of chaos. The one loop, the non-BPS states are more chaotic than the BPS states. Now, this is somewhat similar in spirit to this discussion of black hole string transition, where a black hole can turn into a gas of string as you approach the BPS limit. Now, in gravity, the signature of this slowdown of chaos is the disappearance of horizon. And in this NX4 contest, like IDS5, it would be interesting to understand the gravity picture of this transition better. So I think some discussion by Shiraz this year at strings is relevant for this story. Okay, let me go into the perhaps the most interesting case, the 116 BPS sector. We expect to find strong health in the 116 BPS sector based on many discussion of the Schwarzian description of this sector, etc. Now, however, what's puzzling is that if you just look at the Yang-Mills theory and look at one loop problem, this weak coupling perturbation theory seems superficially similar. Of course, the 116 BPS sector contains a lot more letters, in fact, an infinite amount of letters, but you don't see this qualitative difference that led you to immediately think that this case would be strongly chaotic. So a question for us is, how does this difference arise quantum mechanically? Now, despite very interesting recent progress, including what I showed you earlier, it is still challenging to study the LMRS problem directly in this sector, because to study this projection operator, you would like to find a lot of 116 BPS states, not just one or two such BPS states. However, now in the next part of the talk, I will tell you some indirect argument based on this fortuity phenomena that is recently discovered, which suggests why the 116th BPS sector is completely different from the other sectors. So let me go to this part of the talk, which I connect our story of chaos to fortuity. Now, let me first review a little bit of fortuity discussion for those that haven't seen this story yet. So the idea is that in the angst-4 super-Yang-Mills theory, one can classify BPS states into two types. So this classification arises by thinking about the theory at different n, different rank of the gauge group. In the bulk, it means we think about the theory at different strength of the gravitational coupling in G Newton. Why can you think of it, the theory in such a way? The reason is because of this nice multi-trace basis, which kind of is a very uniform way to think about the theory with different n. So give you an example. Consider this formal expression trace z squared. We can interpret it as an operator in the angst-10 theory. We can also interpret it as an operator in the angst-median theory. Now, in all cases, it's BPS, independent of n. So this is, in fact, the first type of operators, which are called the monotonous operators. These are operators that are BPS for any value of n. So here I'm plotting the anomalous dimensions E minus E BPS as a function of n. Now, it is always 0. At n goes to infinity limit, all these BPS states, by definition, they are light graviton excitations in the bulk. So when we say light and heavy, we're always comparing the energy of the state with n. So when n is extremely large, they are very light. They are graviton excitations. They are non-interacting. Now we can follow these states to smaller n until they become heavy objects. Now this is basically the intuition of how one builds these horizonless geometries by collecting these graviton excitations and forming coherent states of them. In fact, these are conjectured to correspond to all the horizonless geometries in ADS5 times S5. On the other hand, there are these fortuitous type operators, which is completely different. These are operators that are only BPS when n becomes small enough. So if you trace their anomalous dimensions, it's non-zero for n large, but becomes zero when n is smaller than some critical value. Okay. Why can this happen? So the underlying mechanism is, again, these trace relations. Now it comes in a more physically significant way. The idea is that take these operators O, they are trying to follow here. If you add the supercharge on this operator, you don't get manifestly zero. You get some multi-trace expression that is non-zero for large n, but becomes zero due to trace relations when n gets small. So that's the reason why these operators can be non-BPS for larger n, but becomes BPS when n is small. Now, in fact, through index counting arguments, it's known that almost all the states in the 116 BPS sector are of this fortuitous type. So therefore, we can say that we know almost all of the black hole microstates, the 116 black hole microstates of this type, this fortuitous type.
Yiming, can I ask a question?
Please.
So the state that you showed in the beginning, that was this complicated expression for the black hole state.
Yes.
So that would have this property that you could explicitly act some Q on it.
Yes.
And you would see that there is something non-zero, but it's zero when n equals 2.
Yes, exactly. You're completely right.
And this Q operator also has some explicit expression in terms of these letters.
Yeah, Q. Yeah, the nice thing here is that the Q has a simple expression in terms of the the trace of some letters. Yes.
And that's relation.
So when you compute Q acting on O, you can work within the realm of these formal expression, formal multi-trace expressions, without talking about n explicitly.
Right. So that expression for Q does not depend on n.
No, Q does not depend on n.
Okay.
Yeah.
I see.
Good. Good. And how does this connect to chaos? So now in this part of the talk, let me give you some qualitative argument. Now, after this, I tell you a toy model where you can actually test all these qualitative arguments explicitly. Now, let me tell you how this connects to chaos. In sectors without fortuitous operators, let's say the 1/2 or 1/4 BPS sectors, if we follow the anomalous dimensions of these near BPS states, let's say here, I'm not only following the BPS states, but also these chaotic, strongly chaotic non-BPS states. The gap between the BPS states and the non-BPS states never closes as you follow n. Okay, that's in these sectors without fortuitous operators. Now, because of the gap never closes, it's conceivable, at least there is this possibility that the BPS subspace can retain certain distinct features from these non-BPS states. We expect these non-BPS states to be black hole-like. They are generic black hole states. While here, the BPS states is possible to be different. Now, this is not at all a proof, but it's indeed what we see happens in these explicit examples. What is different really is this 116 BPS sector, which is dominated by the fortuitous states. Now here, as you follow n, take n to be smaller, at the regime where n is of order n squared, the gap closes. So the gap closes for small n at the regime where energy scales as n squared. In other words, in fact, at this regime, most of the BPS states in the BPS subspace come from the non-BPS states. So I like to say this as the BPS subspace in some sense lose independence against the invasion of all these strongly chaotic non-BPS states, which we expect to due to black holes. So in other words, during this process of following n, even though these non-BPS states, they lose the eigenvalue chaos, their eigenvalues become exactly the same, saturating the BPS bond, but their eigenvector chaos remains. So the BPS subspace inherits the eigenvector chaos of these non-BPS states. So that's an indirect argument for why here we get to see a qualitatively different picture. So here, in fact, we expect these BPS states in terms of eigenvector chaos to behave similarly as generic non-BPS states. Okay. So this is an indirect argument. So in the last part of the talk, let me tell you some toy model that you can in fact play with all these ideas. So in the n=4 case, it's hard to study the fortuitous states very explicitly, especially it's hard to study them in the large N limit. But there is a toy model where you can study fortuity, this monotony, this invasion of chaos, and all the things you want in the large N limit. So this toy model is in fact not very mysterious. It's a toy model that many people have studied before. It's this so-called Sachdev-Yer-Kitaev model. Now here, of course, I like to study the supersymmetric version of this model, which is the n=2 supersymmetric Sachdev-Yer-Kitaev model, a quantum mechanical model that was discussed by these authors in 2016. I think 2016, yeah. So this is a model that contains n complex fermions. So you have n complex fermions, I running from 1 to n, satisfying this anti-commutation relation. Now, what is the definition of this model? We first construct the supercharge of this model. The supercharge is some random tensor drawn from some Gaussian ensemble, Cijk times psi, psi j, psi k. So it's some 3 fermion term. Now, I like you to think about this random tensor slightly more abstractly as a random 3 form, because it's a totally anti-symmetric tensor with 3 indices. So think of it as a random 3 form. Now the Hamiltonian is simply defined as H equals to Q and Q dagger anti-commutator. Okay, so it's a very simple model. Now there are many nice properties of this model. Let me just list it without telling you how to derive it. First of all, it's a strongly interacting system of fermions. The second feature is that it has many BPS states, in fact, and people have already studied the LMRS for the BPS states in this model and find they are strongly chaotic. So that's nice. A third feature is that this model, in fact, has the same low energy effective description as many of the supersymmetric black holes as governed by this super Schwarzian theory. Okay? So it's sure the same universality class like the low energy effective theory is similar. And that's another nice feature of this model. Now, let's try to understand the BPS states in this model. First of all, the R charge of this model is simply the fermion number. So when I say consider a state with R charge K, I simply mean a state with fermion number K. So that takes this general form. So you take K fermions acting on the Fock vacuum. So of course you have this coefficient which has K indices. I'd like you to, again, think of this slightly abstractly as a K form, O sub K. This nice, the way to think about this is nice because then the Q action, the way that Q acts on a state becomes quite geometrical. So it takes you from a K form, after you're acting on Q, it takes you to a K plus 3 form that is equal to C wedge O sub K, okay? Good. Now, when we try to find BPS states, we want to find states that satisfy these C wedge O equals to 0, but we want to find non-trivial solutions, meaning solutions that are not Q exact. So O sub K, we want it to be not C wedge some other thing. Now, important observation is the following. If you fix K and consider extremely large N, generically, we do not expect non-trivial solutions to this equation. C wedge O equals to 0. By non-trivial, I mean not Q exact. Why is that? So this is easy to see just by counting the number of variables and compare it with the number of equations. What is the number of variables? The number of variables are the number of K forms. while the number of equations, in fact, with generic C basically corresponds to the number of K plus 3 forms. So when N is very large, we know that the number of K forms increase rapidly as a function of K. So you are mapping from a smaller space to a much larger space, and generically, you simply don't get any non-trivial kernels of this map. This implies there are no BPS states with fixed R charge K and large N. Okay, then where are the BPS states in this model? You immediately realize that we start to have many solutions to this equation when N is decreased until N is roughly 2K. The idea is that as a function of K, the number of K form increases and then decreases again. So if I'm somewhere here, by increasing the degree by 3, the number of equations actually decreases, or the number of independent K plus 3 form decreases. So I'm forced to have a lot of solutions to this equation. Now, in fact, on the right of this diagram, you also don't get BPS states because even though you have many solutions to this equation, the solutions are trivial, meaning that they are all Q-exact. And the conclusion is that only in the middle of this diagram, you have BPS states. All the BPS states are extremely concentrated at very special values of R charge. So the width of this window is simply 3 because the supercharge contains 3 fermions. And
or Yiming, could you say again, I just missed why these larger ones are Q-exact?
Here, I didn't give you a very detailed argument, but here essentially is because the number of these spaces just monotonically decreasing. So you can almost reach any states with larger K by starting with a smaller K and act on Q.
I see. So that's the argument that even if you found solutions to that equation, they would be sort of Q-exact.
Yeah, they would be Q-exact, yes.
Okay.
Yeah. Here I'm giving just using the genericity of this supercharge or this random tensor C. Good. And I want to say that, remind you that this interesting feature of R charge concentration is in fact predicted within the low energy Schwarzian effective theory. So I find that very interesting. If you opened up Stanford Wheaton, they tell you that only for 3 R charges, you have BPS states. Now here we are instead interpreting this more microscopically. We are saying, in fact, you can use this genericity argument to say that you only get these 3 sectors. And as a consequence, all the BPS states here are fortuitous because you see the R charge always have to scale with N. So if you fix the R charge and take N to be large, they must be lifted. They must become non-BPS. Now, let me quickly make some comments about this R concentration and then wrap up. Now, as we saw in this toy model, all the BPS states are concentrated to have specific R charge. This is a consequence of the genericity of the supercharged Q, which is, of course, closely related to the quantum chaos of the system. In some sense, the supercharge is generic such that it does not have non-trivial kernels unless it is absolutely forced to. When you reach almost the top of this potential, or this diagram, you are forced to have non-trivial kernels. So we want to draw this connection between this phenomenon of R charge concentration, which is a phenomenon of this Schwarzian theory, to a microscopic feature of the supercharge being generic. Now, I want to make a comment related to angst-4 super mules, which is a new perspective on an old puzzle in this theory. So we think that the supercharge in angst-4 super mules is almost generic. It's not entirely generic because it also has these monotonous states. And because of these monotonous states, as many of you probably know, that Shiraz has been studying these many very interesting gray galaxy solutions that are like black holes dressed by gravitons far away. Forget about all that. If you just focus on the black hole core, we think the angst-4 super mu supercharge is generic, and therefore it's natural to expect R charge concentration. So what is this R charge concentration in angst-4 or in ADS5? it is essentially what people have found in the past that supersymmetric black holes in ADS5 only seem to exist when their charges, the 5 charges, satisfy a so-called nonlinear constraint. So only when the 5 charges satisfy a non-trivial looking equation, you find BPS states. In other words, at least the states that describe the core of these black holes concentrating in very special charge sectors. So we think that this genericity of supercharge provides a more microscopic perspective on this phenomenon, and we hope to understand it better.
Or Yiming, this slide was a little fast for me. So why
Yeah.
does the gray galaxy story relate to the supercharge being not completely generic?
Good. So if like 1 year ago, before Shiraz proposed the supercharge, then we would say that n equals 4 CPR mules exhibits R charge concentration, because only when you satisfy this constraint for the 5 charges, you only on a codimensional 1 slice, you find BPS states. So that's R charge concentration. Of course, let me also say that in the past, people only interpret, well, at least to my understanding, people only interpret the nonlinear constraint as a macroscopic constraint, meaning that it's like sort of a roughly like along this value of Qs, you get BPS states. But what we are saying is really much sharper, like a microscopic constraint. So like we recall this SYK example, only in the width of the charge sectors that have BPS states is order 1 in the large N limit. So it's extremely sharp. Okay. So that's the first statement. If without this gray galaxy story, then indeed you have this R charge concentration. Now, Shiraz is proposing that, in fact, you also get BPS states or black hole solutions outside these codimensional 1 slides. But those black holes would be either black hole dressed by gravitons or black hole dressed by dual giants. So at the face value, you might just say that R charge concentration fails in n for CPR mules because you get BPS states everywhere. But we think there is still a sense, well, I can say a lot more about it, but roughly speaking, we think there is still a sense that if you just focus on this core of the black hole, forget about the stuff that is surrounding it, that is far away, then there is still this phenomena of R charge concentration.
I had missed the fact that the gray galaxies kind of supply this extra coordinate to the
yeah. That is one of the point of the gray galaxy.
One of the points was that there is some instability, and the gray galaxy was the stable point. This.
Right. Yes. But let's say focusing on this BPS context, one of the point is that it supplies these other solutions that do not satisfy the constraint. Okay. I think it's in the upcoming paper of Shiraz. So I guess I don't think it's published.
Okay, I see. That's okay.
But if you look at listen to his talk, he talked about it. Yeah.
Okay.
Good. I think there are still a lot more to understand about like how this really works. But yeah, here I just want to make some comments. Now, well, I'm already kind of over time, so let me just say that there are a lot more to explore in this model.
By the way, Yiming, we are going up to 90 minutes completely fine. That's so don't rush.
Okay, should have told me earlier. I see. Good. Okay, so now good. So in these SYK models, there are a lot more to explore. So let me just briefly tell you some of the things you can do. So one thing is that you can study this interpolation between different n very explicitly, because in this model, it's very easy to understand what you mean by following n. You just decouple some fermions. Let's say you start with 12 fermions, you throw 1 away, you end up with 11 fermions, etc. So you just tune some of the couplings to smoothly to 0. In that way, you decouple some fermions. And you can follow the spectrum in n. And in this way, you can see this, what I qualitatively told you, this invasion of states in action. So you see a lot of these non-BPS states come down and enter the BPS subspace at precisely this n equals to 10. And then they get lifted and come back again, and there are some other states that invade. So there is interesting stories you can study in more detail with.
How do you go to fractional n?
Yeah, that's what I was saying. So there are different ways of doing it. So one way is just by decoupling, gradually decoupling fermions, adiabatically decoupling fermions. So let's say you start with 12 fermions and you take all the random coupling Cij12, you multiply them by lambda and smoothly take lambda from 1 to 0.
Oh, I see.
Yeah, that's actually not the best way of doing it because then it's sort of non-analytic, right? You take it from 1 to 0, then it stops, and then you can't extrapolate it further. So we cooked up some smarter way of doing everything analytically. So analytic, I mean by, so all these curve are analytic function in N.
I see. So
That's
it's
what.
not literally you have some fractional number of fermions. There is some term in the Hamiltonian or something,
Yeah,
which
yes,
interpreting it as decoupling of the fermions.
yes. Only when you are at integer N is literally decouple some fermions.
Okay.
Right. Good. And I just want to say here also that in this chaos invasion picture, one vague argument is that how do you know? Yeah, one question you can ask is how do you know that the non-BPS states do not become non-chaotic as they enter the BPS subspace? Of course, that is as you change n by a small amount, you don't expect the property of the wave function to change dramatically. But here you can check everything explicitly. You can just follow the wave function of these individual microstates and rarely see that it's always like almost resembles a random state as it enters the BPS subspace. So this provides some further evidence of this invasion picture I talked about earlier. Now, what's interesting is also that you can study, in fact, models that contain both monotonous states, so these sort of like horizonless geometries and fortuitous states. Now, let me just tell you like a simple example. So you can generalize a two-flavor model proposed by Haderman, Turiachi, and Zhao, where they introduce two different species of fermions, Psi and Chi. So you take the, excuse me, supercharge to be Cijk, Psi I, Psi J, and Chi bar K. So Chi bar is some annihilation operator. And you introduce some structure into the supercharge by demanding these last two indices to be symmetric, okay? Or you symmetrize these two indices, JK. Now, these kind of models, apart from many fortuitous states, it would have some monotonous states. So here, in fact, you can check that this V acting on the Fock vacuum gives you a monotonous state. It's sort of like a graviton in this model. By graviton, I mean that even though here I just show you one of such state V, such operator V, you can in fact product many of these V together to form much heavier or operators, monotonous operators with larger fermion numbers. Okay, so the idea is that in such toy models, you can study cases where you have many different species of these gravitons, then you can multiply them together and build horizonless geometries. Now you can then compare the properties of these horizonless, well, maybe let me just say monotonous states with fortuitous states, and indeed find that the fortuitous states are much more chaotic compared to the monotonous states.
You mean why in the previous model we could have considered a V which was psi I, psi bar I? So
Which
somehow
one?
that is not a graviton
I mean
operator.
just the angst to two
Yeah,
supersymmetric.
this one, yeah.
And what do you want to consider?
So the V operator could be just psi I, psi bar I, sum over I.
I guess you mean when we say we want to talk about, I guess, a monotonous state. So you want to say that acting on the Fock vacuum as a state.
Yeah, yeah.
Psi I, psi bar I. So you basically act on the Fock vacuum, you just get 0, right? You're talking about a number operator for the fermion.
Yeah, yeah. Mm-hmm.
So it's just
Oh, I
0.
see. You just say it's an eigenstate of that, so it doesn't give you anything.
Yeah, it's you just get 0.
Okay.
You don't get a non-trivial state.
Okay, thanks.
Right. Good. Good. Yeah, so here I'm just showing you one possibility. In the upcoming paper, we explore some more choices, and there are some better ones. Now, other than the LMRS criterion here, because you have such a simple model, you can attempt to look at a lot of other quantum quantities of the states, such as entanglement entropy, etc. And the upshot is that in all aspects, the fortuitous states appear more like random states compared to monotonous states. Good, let me summarize. Let me first revisit the claims I made at the beginning of the talk. So, and hopefully I try to convince you that BPS states can be chaotic, and there is this very interesting notion of chaos, LMRS chaos, and some BPS states are as chaotic as generic non-BPS states. One way to see this is through this chaos invasion. You already see that these states have their roots coming from the non-BPS subspace. Now, there are sharp distinctions between microstates of horizonless geometries, at least many such geometries that are well understood, and black hole microstates. I told you that you can quantify the degree of chaos by this notion of thoughtless time, and they appear to exhibit disproportional degree of chaos. Now, this is further explained or supported by a classification of these BPS states as monotonous versus fortuitous. So let me end my talk by just giving a little bit of outlook. So I think along this line, there are many interesting questions to study. So here, let me tell you just two of them. One such question is that I think it would be fruitful to really test the LMRS criterion for perhaps the most one of the more complex microstate geometries, such as the superstrata in the context of D1, D5 CFT. So one would, even if these geometries do not exhibit the same amount of chaos as black holes, I think it's still very interesting to study within this class of horizonless geometries. Is there already a hierarchy of chaos? Some geometries might be more chaotic than the other. And how do we tell from gravity? I think we currently don't have a very good answer to that. Another idea is to really study the 116 BPS subspace in more detail. So of course, one approach as people are pursuing in the literature is to study the Q-cohomology and wave functions more or less numerically and brute force in small n systems. Now, one might wonder whether you can do some other approximation and try to solve it. A concrete goal one might try to ask is, just starting from the field theory, can you argue that the 116 BPS sector is indeed governed by Schwarzian physics, perhaps already at the one loop level? Now, one very, very naive idea is the following. So you take the supercharge of the 116 BPS sector. Naively, you expand it out in terms of the matrix elements. And perhaps it doesn't look too far away from some sort of SYK model with both dynamical bosons and fermions with some quite sparse coupling, CIJK. Of course, it's not random. It's determined by this trade structure, but perhaps by studying these kind of models with the correct field content, one can then extrapolate some lessons in the actual 116 BPS sector. So I want to highlight there has been some interesting work already in this direction. Now, perhaps more broadly, something that really intriguing, at least to me, in this whole story of fortuity is the fact that this fortuity idea draws a sort of unexpected connection between BPS black hole physics or physics of the supersymmetric states to this topic of null states in quantum gravity or in string theory, which undergoes the name of stringy exclusion principle. So as many of you are perhaps familiar about, there has been many interesting stories of stringy exclusion principle involving D branes, for example, giant graviton branes. Now, this is a case where these null states are in fact related to black holes, so much heavier objects. So I find that very interesting. Just to make what I say slightly more concrete, let's say that instead of following these fortuitous states, following this operator O and see how it enters the BPS subspace, we can choose to also follow its super partner. So instead of following O, let's follow QO, okay? Now, when O is non-BPS, QO, as I said, is just the super partner black hole microstate. So it has exactly the same energy, and it's just another state that follows exactly the same trajectory. But what happens is that this super partner black hole becomes a null state at this critical value of n, and stays a null state ever since. So one can say the following, that as each fortuitous state is born, or each fortuitous state enters the BPS subspace, its super partner black hole in fact becomes a null state. So that is an interesting feature. And in some sense, we can say that this trace relation that appears on the right-hand side of this equation, QO equals to this trace relation, we can in fact understand this trace relation in the bulk as the extrapolation of these black hole microstates. And these are the in other words, these highly complex trace relations appearing here, in some sense, is dual to this phantom black hole, these black hole microstates that become a null state when you decrease n by 1. So I found that quite intriguing. I hope to have more words to say about it. And with that, I'd like to thank for your attention.
I already asked a lot of questions. Are there people have questions on Zoom? If not, I have a question here. So here you're thinking of O and QO both has black hole microstates in this picture?
Yes, yes. Well, we know that, right? O is a black hole microstate, and QO is just another black hole microstate in the same multiply.
In the super multiply, okay.
Yeah.
And so these trace
black hole microstates. Yeah.
Yeah. So these giant graviton trace relations first appear when the energy is order n+1, right?
Yeah, yeah.
But these ones are like trace relations with n square amount of.
Exactly. And here I'm saying the way that you understand it in the bulk is a bit different picture.
Yeah, I see. So you're saying maybe there is some qualitative difference between trace relations that are of the form trace of matrix to the power n+1 and these n square type of trace relations.
At least like this, at least this family of trace relations that are smoothly connected to these black hole wave functions. So we expect them to be some multi-trace that it has extremely high complexity, very, very complex trace relations. They seem to be due to some sort of, well, I don't really know how to think about it in the bulk, but it's some continuation of this black hole geometry that in fact correspond to null states.
But do we get some insight by looking at the trace relation in the explicit state that you showed in the beginning? So there, the right-hand side is some explicit operator, right? For the SU2 theory.
Right. Yeah, I mean, I'm not sure by insight, what exactly do you want? I guess.
I mean, it's a vague question, so you can answer.
I guess it's a pretty complicated expression. Well, as complicated as you can get probably here. So that's some trace relation. I guess I'm not sure. Yeah, what's the right question to ask here? Okay. I think, yeah, one question, very, very vague question that I want to ask is, so maybe let me go back to my last slide. So you see here, this picture might not seem really striking to you. Just one state becomes null. That might be fine, but combine this with this R charge concentration in the earlier part of my talk. What we think really happens here is that exponentially many states become BPS at exactly the same value of n. So that actually means that exponentially many low-lying states in the spectrum become null at exactly the same time. That makes me feel a little bit worse, or a little bit more intrigued, because you see, exponentially many states, you sort of you should describe them by some bulk variables, maybe like some black hole geometry. So that's sort of like some continuation of that black hole geometry just becomes only described null states. It's a bit.
But how is this comment related to R charge concentration?
Yeah, R charge concentration is saying so. Good. How is it related to R charge concentration? Now, one question you can ask about this fortuity picture is that when do these fortuitous states enter the BPS subspace, right?
Yeah.
You might think, okay, maybe some enter later, some enter earlier, okay. But
Yeah.
if you now recall the R charge concentration story, the idea is that if you fix n and vary the charge, only for extremely special R charge you have BPS states. At least let's forget about this subtlety in n equals to 4.
Yeah.
Only when R charge equals to some special value you get BPS states. Now, another way of saying this is that if you fix the R charge and vary n, only when n is equal to some special value you get BPS states.
Right.
So that in fact means that there is a special value of n. Also here, of course, you fix the charge to begin with. So
Right.
then there is some special value of n where a lot of states become BPS. And then if you extrapolate further, they just almost immediately all become null states also.
I see.
Yeah, so yeah, in some sense, these supersymmetric black holes are really like a transient phenomenon. It's yeah, it's pretty sharp in the large n limit. And it's yeah. Yeah, so then you have many of these states become null state at the same time. I'd like to have better collective field understanding of these, maybe in terms of G sigma action, these kind of things.
I see. That's an interesting interpretation. I think this I had not heard before. This.
Oh, thanks. Yeah, we can discuss more if you're interested. Yeah.
Okay, thanks, Yiming. Ramesh, do you have it?
Okay, maybe let me stop sharing.